Okay, in this video, we're going to somewhat limit ourselves on how much we're doing with graphing these polar equations. I want to say first off, in the TI calculator, 83, 84, or 89, they all are pretty similar. You'll go to mode and switch from, oh, I forget what our rectangle, I think it says like f of x or something, but you'll see it. You'll find polar, there'll be options for parametric, polar, and something else, and just select polar. And then when you hit the y equals button, it'll no longer have y1, y2, y3, it'll have r1, r2, r3. And when you use the variable button x, t, theta, end, it'll automatically put thetas in there now. And then I also encourage you to open up the window, the settings, and you'll see all sorts of values in there. Usually don't change them, you'll be all right, but if you have troubles, you could Google how to change these settings as well. I'm not going to explain it in this video. I think geogebra.org also does a very good job, and there's minimal interaction you have to do in there. So we will explore an example with GeoGebra. Okay. Before both of those though, let's kind of look at the process that's going behind a calculator when it does the work for us. So just like x and y, right? If I had a function, y is a function of x, then, or x is a function of y, either way, it is choosing an independent variable, in this case theta. It's choosing many values for theta and computing these, I mean millions of values within seconds, right? And computing these to draw us a graph. So if I substitute theta, and just like xy, like a good starting point, we usually did, -2, -1, 0, 1, and 2, like that, to find y. Same thing here. I want to place 0 in the middle here, and then kind of think of a few values, all right? So it might also be handy to have our sine chart like quickly at disposal. Sine theta, since I have all sines, right? And 0. So sine is the y value. Remember, sine is the y. So 0, and then, so pi over 6, pi over 4, pi over 3, pi over 2. Okay, and then from there, remember, outside that first quadrant, they just switch values to negative. So if theta is 0, then sine theta is 0, so 3 times 0 is 0. Right? We have 3 times 0 right here. We'll choose just a couple values. Like, I know this angle, all of these are in quadrant 1, so we'll just do pi over 4. Okay, and we'd have 3 times root 2 over 2. Okay, 3 root 2 over 2. And we would want a calculator to start approximating these. And then let's go up to pi over 2 for an angle. So we just have 3 times 1. All right. Now as I move forward, sine only ranges from 0 to 1, right? So they're going to go lower. So let's look at the angle 135 degrees, so 3 pi over 4. And I'm going to get 3 radical 2 over 2 again. Okay, and then when I go to pi, sine of pi is 0. Okay, and so forth. And actually we'll do one more. When I go down to quadrant 3, 5 pi over 4, I would get negative 3 root 2 over 2. Right, and then 1.5 pi, 3 pi over 2. Sine is -1, so I get -3, and so forth. All right, so when we go to the negative angle, negative pi over 4, sine is again negative, we get -3 root 2 over 2, and then negative pi over 2 is the same thing as 3 pi over 2, right? We're here, and so we get -3. All right, let's kind of start picturing what's going on here. I'm going to draw just this xy. I think I remember what this graph looks like, but kind of, visualizing all these thetas and r's is a lot more challenging than xy. So I don't know where we're going to end, is my point. I don't know if it's going to go down in quadrants 3 or 4, or my thought is I think it stays in quadrant 1 and 2. Let's check it out. Let's graph a few of these easy ones. 0, 0. Remember, that's not xy, that's the angle 0, and I have a radius 0, okay? Pi over 2, 3. Let's graph that one. So the angle is pi over 2, so that's 90 degrees, and I go up 3 units. So we have that point. Okay, pi 0. That's an easy one to graph. If I do an angle of pi, right, but radius of 0, I'm also still at 0, 0. Negative pi over 2, let's do this one. Negative pi over 2, -3. So I do the negative angle, -90, but then -3 brings me right back up to here. So 5 of those points, I really only got 2 points drawn, right? It doesn't help much. So let's try some of these in between. The pi over 4 gives me 3 root 2 over 2. So one, I'm trying to approximate here, it's going to be like not even 2, right? 1.5 times 1 point something. At either rate, pi over 4 I know is this angle, and I'm going to go somewhere like eyeballing it here. I don't think it's quite 2, but we could put that in a calculator. I don't really care for this example. Okay, 3 pi over 4 would give me the same r, so here, I'm like somewhere around here, I guess. Okay, so I graphed those two. Let's look at this negative angle. The negative pi over 4 is this angle here, but then I have a negative radius, so I'm right back here again. Okay, I think you could see how tedious this would be, and this last angle I think gives us another point that's exactly the same. 5 pi over 4 is here, and a negative would be here. It didn't really do much at all, right? So let's just use a couple of these values that I have here and then symmetry. So pi over 6 is, this angle here, and I get 1/2, but multiplied by 3. So if theta is pi over 6, I'd get 3/2, so 1.5. And again, we could only eyeball a radius anyways, right? Diagonally. I know that that length is 1.5 that I just drew right here. Okay. Let's use the pi over 3. So I ran out of room. If theta is pi over 3, then I'd have square root of 3 over 2 times 3, so 3 times root 3 over 2, which is larger than 3 root 2 over 2. So when I go to do this angle, it's going to come out just a bit more. Right now, anything else, I kind of need a calculator. I don't know the value of something slightly less than pi over 2, but greater than pi over 3. Like, I don't know. All these values in here are not on the unit circle. But I do know that sine range is only right between -1 to 1. So therefore I know it cannot be greater than 3. And as we approach pi over 2, it's approaching 1. As we approach 0, it's approaching 0. So as a visual, I could kind of see what's happening. The smaller the angle, right, the smaller the radius. The larger the angle up to pi over 2, it's coming close to 1, which is coming close to a radius of 3. So therefore, this should be circular over here, and because of symmetry, it's going to do the same thing over here, right? But that's a ton of work. So let's jump over to GeoGebra. That's the idea behind it. Again, it's calculating all of those points, like, thousands of points in between even just 0 to pi over 2. So, all right, let's hop on GeoGebra. All right, I have a couple that I typed just to save some time, but don't worry, you don't need to memorize like how to type that a equals curve 3 cosine 5 theta, whatever all that stuff is. Let's do the one we were just doing, right? 3 sine theta. And what it does is it generates all that for us. Okay, I didn't type any of that stuff. I know there are options we can play with, but we're just kind of looking at the basics. So we're going to literally type R, okay, and then there's some different tabs here. Okay, so I need equals, R equals 3, and then sine theta. Sine is in this function right here, sine, and then I need theta, and I don't see it here, so what I did is I went back to the ABC, and there's a Greek button in the lower left tab here, and then I put theta. Although I didn't test, like, can you use another value? I tried X before and it didn't work, but I don't know if there's been an update. Okay, and that looks like the graph we had, right? So all I do is I click off of this, and then notice it generated that whole curve 3 sine theta. I didn't do any of that. Cool, so that sketch we had was pretty good. So let's look at the power of some of these curves that we can do with polar equations. All right, so we did that one. I'm going to unhighlight it, and let's look at this top one. So I typed R equals 3 cosine 5 theta, and then it generated all those other variables for us. And look at that graph. That's pretty cool, right? And actually what it does is, for that one, the 3 is the radius, and cosine the 5 actually determines the number of petals there are. But, I'm just exploring. There are some really, really cool graphs that can be created in polar coordinates. So you can mess around with it. This middle one here, that was the one we did. Here I did R equals 2 minus cosine theta, and it put this little dimple over there on that circle. The values of theta and the 2, whatever, if I put a coefficient in front of cosine theta, every little change will change these graphs. Play around with it, pretty cool. There's all 3 at once. GeoGebra is an awesome tool.